Hello everybody, welcome to my YouTube channel. I'm Krishna Gopal. I completed my masters this year from Indian Statistical Institute, and in this video we're going to talk about the one of the simplest model in the machine learning known as linear regression. Also we're going to see in this video what are the interviewer can ask a question from here if you are applying in the banking sector or in some kind of a trading company if you are visiting and you have an interview there. So what to prepare from this topic, what interviewer can ask the question from this topic, we're going to discuss in this video. Also I'm going to share what the question I face in the interview and how to give the answer. So we start this chapter from the starting, so if the newcomer also watching this video, it will be helpful for them. Plus who is preparing linear regression as the before going to the interview, they also know what are the questions they can expect from this topic. So let us start the video. The linear regression is one of the oldest technique in the machine learning which used to predict the quantitative response. I mean to say here quantitative response means your target variable consider the values coming from the real line. So the linear regression is one of the oldest technique in the machine learning. Let us suppose we are going to purchase the new home in the new city, and we want to see the estimated price of my new house. For this, if I went to the statistical analyst who show me the behavior between the number of square foot and the price of the house, it will be easy for me to see what are the square foot, how much square foot corresponding to the house of a price. So when I go and told to statistical analyst I want to purchase the home, he show me the graph like this. Suppose this is the y-axis and this is the x-axis, and here we tell it is a number of square foot, and here we tell it is a price of house. So say here the 100, here 300, here 500, here 700, and suppose this is the hypothetical number. So here 10 lakh, this is 30 lakh, and this is 50 lakh. So now if there is a linear relationship, between the number of square foot and the price of house, then the job become easy. Say the line is this, almost it is linear, and I want to purchase the house of 500 square foot. So this task become very easy now. So near about for more than 45 lakh I need in my budget to purchase the house in the new city. Similarly, if we talk about the new example, another example like I want to predict my numbers in the mathematics exam versus how much hours I should study to how much hours I should practice the mathematics in the notebook. So again the graph is I have the graph like this. These are the two examples we are discussing before starting this topic in the deep. Say here the time is spent, the time, and here the marks. Because the more you practice on the mathematics, more your fundamentals become clear, and it's easy, we can get the more marks. Suppose I study 5 hour, I study 10 hour, and I study 15 hour, I get 30 marks, 60 marks, and here I am getting the 90 marks. And if again I have the linear relationship like this, again I can predict okay, if I study the 15 hours, if I study near about 15 hours, I can get more than 90 or more than 90 marks I can get in the exam. So these are the two examples we discussed before starting this chapter. One is the price of house, another is the marks in the mathematics. So what we seeing in both the example, if our curve, if our graph have a straight line, then our job become very easy to predict the response. So say here in the number of square foot is also known as my predictor, and the price of house is known as my response. So predictors are also known as independent variables, and response known as the dependent variable. Okay, when the first assumption of linear regression is that this model assumes there is a linear relationship between the predictors and the response. That means, as we studied earlier in our school days, we know the straight line equation. If I want to show this model mathematically, I can write the straight line equation like y is equal to beta naught plus beta 1x. Okay, we can write phi is equal to beta naught plus beta 1x. This is the straight line equation we earlier studied. Mathematically, we define y is equal to beta naught plus beta 1x. X are known as the predictors, also known as the independent variable. Y known as the dependent variable. Beta naught and beta 1 are the model parameters. We say unknown coefficient. If I know, if somehow, if I get to know the value for beta naught and beta 1, it's easy for me to predict the y, and prediction we present with cap. So it's easy to know y cap once I know beta naught cap, beta 1 cap and x, because I know the value of x. My job now to predict or estimate the value for beta naught and beta 1. These two terms known as the model coefficient or model parameter, and generally defined the beta naught is the intercept and beta 1 is the slope of line. So how to measure the beta naught and beta 1? This is the one of the next question we have, how we can measure the beta naught and beta 1 in the model beta naught and beta 1. So there is a old technique and the much more popular technique in the statistics known as the least square. So once we use the least square technique, we can choose the estimate for beta naught and beta 1. When we are predicting the y cap for y for particular x, is equal to x, there is a chance that we can see some difference between the observed y value and the predicted y value. Say we can see the curve like this. If this is our curve and we have the regression line like this, we can see here, if our we take this color, if we have this our observed here, observed value for response here, and in the regression line we can see this values here. So the gap is defined as residuals and denoted with EI. So once we use the least square estimate technique to estimate beta naught and beta 1, we actually by this regression line, by this fitting line, we actually calculate the sum of square of the distance between the observed and the predicted value. That distance is known as the residual, denoted with EI, and also we can define the residual sum of square, that is popularly known as RSS, and we can write as E1 square plus E2 square up to En square. More generally, RSS is square up to en square. So we can write y1 minus beta naught minus beta 1x whole square up to yn minus beta naught minus beta 1xn whole square. Now we choose beta naught and beta 1 cap in such a way that we have minimum. So the least square approach help us to choose beta naught and beta 1 in such a way that we have residual sum of square is minimum. So moving next in this topic, when we tell this model assume the linear relationship between the predictor and the response, and this is the one of the basic assumption in linear regression, and we define the y is equal to beta naught plus beta 1x also. This is the straight line equation, and we tell this is our model equation, but this equation is not probably a linear relationship, because there are some observation which can make a variation in our response. There are some measurement error. So by considering these two factors, we need to add one more term that is known as error term. So we have to be modify our this equation to y is equal to beta naught plus beta 1x plus epsilon. We denote this error term with epsilon, and this error term assume the mean of the error term is 0 and have a constant variance sigma square. Now here is one of the most important question which I face in many interviews. They first ask me what is a equation for linear regression model. I go and tell y is equal to beta naught plus beta 1x plus epsilon. There is an error term, and I just add the error term, have a mean 0 and a constant variance sigma square. More generally, we tell the error term follow the normal distribution. So one of the most important question, if you are facing if you are appearing for any banking sector as a data scientist profile, the first question they ask you, what will happen when this error term does not follow the normal distribution? What will happen to our linear regression model? So there is a one full mathematics behind it if error does not follow the normal distribution. But generally when we appear for the interview, mostly we not study that much deep. Generally I not study that much deep at that time, but when they ask the question, so I have no clue like what will happen when the error term does not follow the normal distribution. Is basically simple assumption, but then I study about it and I try to explain also to you guys if you face this question in the future, so you can save yourself. So the question is, what will happen if error does not follow normal distribution? Now I clear the 2 points here. If error does not follow the normal distribution, then there is no effect on beta naught, on estimating beta naught and beta 1 cap. First point, there is a no impact on beta naught and beta 1 cap if error does not follow the normal distribution. But yes, better, and we can predict the y cap easily. But if error does not follow, so we will some hypothetical test, hypothesis and confidence interval have a huge impact. So now next question may be, which hypothesis test you are talking about? Which hypothesis test we build in the linear regression? When we tell there is a linear relationship between the response and the predictor, we assume there is some relationship. So let's check this hypothesis, like there is a relationship between the response and predictor, or there is no relationship between response and predictor. So we define our null hypothesis as, I'll just stick this. So we define null hypothesis as H naught, that there is no relationship between x and y, and we define the alternative hypothesis with HA, there is some relationship between x and y. Now mathematically we can write this: H naught beta 1 equal to 0, H1 is beta 1 not equal to 0. Because we have the linear equation y is equal to beta naught plus beta 1 x plus epsilon. Now if beta 1 is 0, there is no term x, there is no predictor, so there is no relationship between the response and predictor. Now if beta 1 not equal to 0, then there is some relationship between the response and predictor. Now to reject this null hypothesis that beta 1 equal to 0, to reject this null hypothesis we need our beta 1 is significantly far from the 0. How much it will be far, that is a point here. So to calculate how much it should be far from the 0, we calculate the standard error for beta 1. Assume you know about what is a standard error, and if don't know, means we will discuss in the next video because it will be out of context for this video. So we calculate the standard error for beta 1. For just little explanation I want to tell. The standard error actually measure the average distance between the observed value. Suppose this is your observed value and this is your the regression line. So it basically measures the average distance between these two, and more the distance, more the error in the model. So we calculate the standard error for beta 1 to check how much it will be far from the 0, because we can reject the null hypothesis when we have beta 1 not equal to 0 only. So we define one t statistics also. We define one t statistics as beta 1 divided by standard error of beta 1 cap. Now if error say now if we reject null hypothesis, to reject null hypo, T1 should follow the student T distribution. T1 should follow T distribution with n minus 2 degree of freedom. Okay, so if it follow the T distribution, then we can say the beta 1 is actually far from the 0. What I mean to say mathematically, how we can write the mod of T1 actually should be greater than T of n minus 2 alpha by 2. Why this alpha by 2 here? I have to alpha by 2, why it is? Because the T distribution also have the bell-shaped curve. It is also okay, we can delete it. Yes, so actually the T distribution shape is also like this is like T distribution. We have our alternative hypothesis beta 1 not equal to 0. That means it's talking about the two-sided distribution. So this reason is alpha by 2 and this reason is alpha by 2. That's the reason, that's the point we are using here, alpha by 2. So this mod of t1 is greater than t of n minus 2 alpha by 2, and we calculate this value by seeing the, if we are doing theoretically, we see this value with the help of t distribution table, which is mostly given in the textbook. And if our value of mod of t1 is greater than this, we are rejecting the null hypothesis. That means we are assuming there is some relationship. Also, this expression equivalently we can write with the help of p value, like mod of, okay, we can write p of mod of t1 should less than alpha, where alpha is your significance level. And already I explained why we are assuming, why we are taking here alpha by 2. This is the significance level. Okay, so if that our t statistics follow the t distribution with n minus 2 degree of freedom, we are here rejecting the null hypothesis, and we are assuming there is some relationship between the response and predictor. So if error does not follow the normal distribution, then here this t statistics which we are defining, like it follow the t distribution, it does not follow the t distribution. There is impact here if your error does not follow the normal distribution. Another thing what I spoke is about the confidence interval. So similarly the confidence interval, okay, we take different color. Confidence interval, if error does not follow the normal distribution, then we not have the bell-shaped curve, we have the highly skewed distribution. That means we have a highly skewed distribution. So when we have this highly skewed distribution, which confidence interval I am talking about? Suppose we have the 95% confidence interval that for beta naught, like beta naught cap, like beta naught cap plus minus t of n minus 2 alpha by 2 into standard error of beta naught cap. So this interval assume there is a 95% chance the estimate value for the beta naught lies in this interval. But if error does not follow the normal distribution, then this interval, then actually we have the highly skewed distribution which not have the equal probabilities at both of the end, and we are impacted this confidence interval. So there is a two major drawback if error does not follow normal distribution. Just before that, this confidence interval have now not have the bell shape, so we have the highly skewed, and we are not assigning the equal probabilities to both the end. That will be dangerous to us. So the two things will impact. Now to check like your distribution, how you know like your error follow the normal distribution, or your linear regression model which you going to be use, it follow the errors of that model follow the normal distribution. So either you can plot the histogram for this, or you can plot the residual plot for this. But in this video we talk a little bit more statistically. We can measure the skewness and kurtosis. There is a two term. The skewness actually measure the symmetry. It measures the symmetry of the distribution. So if our distribution have a normal distribution, then the skewness coefficient is 0. And what is the kurtosis? It actually measures the tailness or peakness. So for the normal distribution, we tell the kurtosis coefficient is 3.0. So if these two conditions are satisfying, we generally say there is our underlying distribution is a normal distribution. Now you know your distribution is not a normal. Now how you can recover from this problem? So for this there is a simple approach known as the transformation. We can use the transformation of the dependent variable to some other variable which can follow the normal distribution. because once error follow the normal distribution, we have the linear relationship, then any linear relationship can follow the normal distribution. So we can use the transformation technique, like we can use the sine curve, we can use the cosine curve, we can use the logarithmic function, which can make our dependent variable to follow the normal distribution. So this is the one I think this is the second assumption we talk, that what will happen if error does not follow the normal distribution. If you understand this, then I guarantee like there is no more question can come, and you will be more confident while speaking that your error, what will happen when error does not follow the normal distribution. Now moving to the another assumption of linear regression. Now moving to the another assumption of linear regression, we also assume the errors are uncorrelated. The error should not have the correlation nature between them. So the another assumption we assume here of the linear regression, that the errors are uncorrelated. What are the correlated error? When, why they occur, when they occur, in which process they occur? So like this, if interviewer is more interested to ask your fully mathematical and behind knowledge, then he can ask this question. So whenever we have the time series base process, whenever we use the time series base data set to apply the linear regression model, we have this error. When any physical process, or say when any biological process, like you are measuring the plant growth in every time period, then there is a chances there is definitely chances the errors are correlated, but our model assume the errors are the uncorrelated. What will happen if the errors are become correlated with each other? That means your model is missing something, missing some important information which it should capture, which it should capture if the errors are uncorrelated. Now suppose that EI is the error and EJ is the error. This occur at time t1, this occur at time t2. Now this error is EJ is also correlated with EI. Now at time 2, our model failed to capture the information which it should capture. So again, more mathematically, if we go, what will happen if errors are uncorrelated? Sorry, when the errors are correlated, it also affecting our confidence interval. Definitely, we are using the standard error in the confidence interval, and to measure the actual what the error can impact, we measure from the standard error, right? So that is our one point here. Now what we can do, how we can be overcome from this problem? We can use, there is a general weighted least square. There is an approach we will discuss in another video about it, so that can help us to overcome from this problem. Okay, so these are the three most assumption we discuss in this up to this time. So moving to the next assumption is the about the heteroscedasticity. Your data should not have heteroscedasticity, means your variance of your error term should be a constant. It's not like your error term like okay, we can say the each observation on the dependent variable have a to the one of the most important assumption, that each observation on the dependent variable have the equal weightage. What I am talking, our data should have homoscedasticity, not heteroscedasticity. That means our data, this is the another assumption. This, I think this is the fourth assumption we are discussing here. Our data, suppose this is, so our data is like this should be, okay, it's not should be like, you can say like this. So we want like this. So what it is, the each observation on the dependent variable have a equal weightage in the linear regression model. That means the variance of the error term should be a constant. If the variance of the error term is not constant, that means we are giving the more weightage to the subset of data, and we are violating the basic how we estimate the coefficient. We not estimate the that kind of we not have the unbiased, or we can say we not have the minimum variance of regression estimate if the variance is not constant. Let we discuss in the starting of the video, we discussed the second example, the mathematics marks versus the time is spent to practice the mathematics. So suppose if the variance of that error term is not constant, if you study 5 hours, then also you are getting the 90 marks. If you study the 15 hours, then also you are getting the 90 marks. That means our model is missing something. So this is the most important assumption. We should check first, there should be a homoscedasticity. There should not be a heteroscedasticity. Okay, so, or we can say the variance of the error term should be a constant. If not happen, then we should use the weighted least square. This is another approach. By using this, we can be recover from our this failure of this assumption. So these are the basically the four assumption we discussed. The linearity in the linear regression model. What will the error should follow the normal distribution. The error term should be uncorrelated, and fourth one, the variance of the error term should be a constant. Now moving to the fifth one is a very important, and there is I will definitely do another video for that, but completing this assumption here, that should be your multicollinearity. First we define what is a collinearity. Collinearity, y is equal to beta naught plus beta 1x plus epsilon. Okay, now if our predictors, if one or more our predictor should not be correlated with each other. If the predictors are the correlated, then definitely we are violating the linear regression model assumption. That means there should not be a collinearity in your data set. What will happen if there is a collinearity? This is another question most of the interview I face. What will happen if there is a collinearity? If your two features are the collinear, then what is the problem actually? Actually, if there is a collinearity, it increases your standard error, and if the standard error increase, and then we are fail again to build our good confidence interval. Also the collinearity, also the collinearity make us in that situation where we are failed to reject the null hypothesis, and then we should tell there is no relationship between the x and y. Then what is the point? We are building the linear regression model. Now now you are just thinking how the collinearity can increase the standard error in the linear regression model. This link is connected with the another important term known as the VIF, that is the variance inflation factor. Actually, when three or more than three predictors are correlated with each other, we say that situation is a multicollinearity. And to measure the multicollinearity, we use the variance inflation factor to measure how much multicollinearity in the data set. If there is a multicollinearity, definitely we are violating again the assumption. And simple formula to calculate the VIF is 1 divided by 1 minus r square. If VIF greater than 5 or greater than 10, we say there is a problematic collinearity in your model. So you should rectify your model again by either you can drop that predictor from the model which actually giving the more collinearity problem in your regression model. Because what will happen when suppose x and y, there are the x1 and x2, there are the two predictors. Now they are the correlated with each other. So how much x1 increase, that much x2 increase. Now how we see what they impact on the response. So that is basically we should be recover from the multicollinearity problem also when we are building the linear regression model. And the next very simple assumption is the outlier. There should not be outlier in your linear regression model when we are going to build linear regression model. So these are the most 5 important assumptions in the linear regression model we assume before while we are applying the linear regression model to any data set. Basically we check how we can recover also, but these all the points I talk in this video is more towards how you can give the answer in the interview and what the question he can ask you from the interview. So before finishing this video, let's do a small summary so we can understand broadly what we discuss in this video, and you can have the how much you can gain from this video you can gain. And if still there is some point which not clear, like I talk about the hypothesis testing or I talk about the confidence interval, you can let me know in the comment section. I again can in the next another video I can again discuss the points or try to make you more clear in the comment section itself. So that's your job, you should do. So I know, like, okay, you are facing the problem here. So let's do one summary before we are closing this video. We mostly discuss the what are the assumptions in the linear regression model. So the first assumption should be a linearity, that your response variable and the predictor variable should be a linearly should have the linear relationship between them, then only the linear regression model work very well. Second is the error follow the normal distribution. We already discussed what will happen when the error does not follow the normal distribution. Third is the errors are uncorrelated with each other. Fourth, variance of the error term should be constant. Fifth, there is no multicollinearity. Sixth, avoid the outliers. Okay, so these are the basically 6 most important assumption before we build the linear regression model. Hope this video try to clear your some concept behind the linear regression model assumption. In the next video I will talk about some most important question which I face in the interview and how I give the answer and how actually it should give the answer in the interview. I try to help from my side best. I try my best to clear your doubts, and also let me know in the comment section if something and some assumption at some point is not clear. I try to do again I try to explain in the video. And thanks a lot for watching this video. This is quite long, but we try to make short in the next time. And thanks a lot, and let me know if you have any doubt. Thank you.